Hello all, this is the video project by Group 13. Our topic is Kramer's opacity law. In this we will be discussing the density and temperature dependence of opacity by four primary sources.
Intensity or the cross-section of light interactions with matter determines the opacity of the matter. At high temperature, the sigma nu is essentially constant of temperature, but at somewhat moderate temperature, the sigma mu is a function of temperature. In order to model the behavior of K nu with temperature, we have to invoke the local thermal equilibrium, which paves the way for relating these microscopic interactions with macroscopic variables. The four primary sources of opacity are free absorption and Bremsstrahlung emission, the free bound transition, the bound transition, and scattering by the electron gas. The temperature dependence essentially comes from the phase space of the scatterers or the momentum space of the scatterers and the temperature dependent densities of certain atomic species. At very high temperature, the opacity gets decoupled from temperature, as we can see from this equation, and essentially the opacity is constant of rho and temperature. In the free scenario, according to Lamar's radiation laws, the emission by an electron in a thermal Bremsstrahlung can be modeled as 1 by v square times an integral. The integral comes from an impact parameter averaged over all the electrons hitting the ion. The total rate of emission can be written down as the electron flux, which is any times velocity, hitting ion density times the energy emitted by an electron, which is a velocity dependent term. And we are averaging this whole total rate of emission across a velocity distribution. If we are counting only the rho, t, and nu, we can see that we can essentially decompose this whole total rate in terms of rho square, t to the power minus half, and times an integral. In the free scenario limit, we can approximate this integral like this, where the xi min is an impact parameter term and is essentially independent of rho, temperature, and nu. So finally, we have the total rate depends on rho square t to the power minus half times an exponential decay. Now, if we write the total rate of emission in terms of the emissivity of the matter, we can see that rho j becomes the total rate, and using the blackbody distribution and under local thermal equilibrium from the Kirchhoff's law, we can relate the emissivity with the opacity, and we have this total relation that frequency dependent opacity goes like rho times frequency minus 3 t to the power minus half and 1 minus some exponential decay factor.
Now we want to find the Rosalind mean for the opacity. In order to do that, first we find the Rosalind mean over all the frequencies for absorption coefficient. And from this relation where absorption coefficient equals density times opacity, we can get Rosalind mean opacity for the stellar matter. And to pictorially describe the free scattering, you can look at this diagram. The electron comes from this path and it interacts with this ion, and as it gets attracted, the path is deviated to this direction, and due to this it produces breaking radiation or the Bremsstrahlung radiation and emits a photon. That is basically free scattering. And if the free contribution were all that existed, then the Rosalind mean opacity would take this form, and this is how it will depend upon density, temperature, and frequency through this integral. So this integral can be solved by this particular substitution where h nu by kT is put as x, and as we solve it, we finally find this relation or the proportionality where temperature and rho dependence are 7 by 2 and 1 respectively, to be precise minus 1, and this particular integral found by this substitution is nothing but a standard integral called Stromgren's function, which is a constant value in this case. If we put that value, we find this particular relation where opacity is proportional to rho times t to power minus 7 by 2. This is our Kramer's law derived from free contributions. So if we take a numerical fit in CGS units for the ionized hydrogen and helium with mass fractions x and y respectively, where the main scatterers are free electrons, the Kramer's law takes this form.
So another major source for Kramer's opacity is the boundary opacity, in which case an incident photon has high enough energy to ionize an atom to free an electron. So in this case, the cross-section absorption goes like this relation, where L is the principal quantum number and nu is the frequency of the incident photon. And in this case, this relation must have to be satisfied, or the incident energy must greater than the ionization potential, and we only count that ionization potential of that principal number which goes like background temperature. So as soon as we get this cross-section absorption, we can derive the total absorption coefficient, which goes like this relation, where n is the number density of the unionized atom in the state of L. So if we calculate this goes relation like this L square. So to get the relation between the unionized number density and the ionized number density and the number density of electron, we need to use the Saha ionization condition, which goes like this, and this unionized number density simply relates like this relation. Okay. So as soon as we get this term, we can substitute this term into this equation to get the total opacity of frequency dependent. So as we stated earlier that this ionization potential must be proportional to the temperature. So this square bracket term basically independent of temperature. So our this term rho k nu term basically depends on this. So basically our frequency dependent opacity goes like this one, as fixed this case. So if I take the Rosalind mean, we can get this sort of relation, where this Rosalind mean bound free opacity goes as rho and to the power minus 3.5. Okay, so this was the case for one single type of atom, and if we take all kinds of atom like hydrogen, helium and others as well, so we can get this relation, where this factor 1 minus x minus y is basically counts the all other mass fraction of all other atoms. And this figure, where we can see that there is a sharp edge of nu to the power minus 3, because as I stated earlier, the cross section varies at nu to the power minus 3. So that is all for bound free opacity.
Now let's look bound contribution to the total opacity term. Since there are a very limited number of incompletely ionized states in the deep interior of the stars, their contribution to the total opacity is very less actually when we compare to other contributions. When the temperature is in between 1000 and 10,000 K, there is a very non-trivial contribution to the total opacity term, and which is given by H minus ions. In this temperature range, the H atoms can capture electrons from the alkali metals and can become H minus ions. When we look at the quantum mechanical analysis of H minus ions, we can say that for the second electron, there is a 0.754 electron volt potential to get ionized. So since this potential is very less, they can easily become ions and they can contribute to the total opacity terms. So at this temperature range, the most dominant term to the total opacity will be given by H minus ions.
So assuming local thermodynamic equilibrium to be valid, we see that the alkali metal releases an electron which is captured by the hydrogen atom to become H minus ion. And since this ionization potential is about 0.754 electron volt, which corresponds to thermal background of 10,000 Kelvin, so the opacity, bound free opacity, is given by this relation, in which we see that the density of H minus and density of electron is given by these two equations, these two relations, which comes from the law of mass action. And we see that the H minus and density of H minus and density of electron depends on K1 and K2, and so we get this relation where there is a deviation from the simple T to the power minus 7 by 2 dependency of temperature on opacity through K1 and K2, and hence we get a disruption from the simple Kramer's law. So now we will explain this graph of K kappa versus temperature. So we see that for this low temperature range, the H minus opacity relation will be dominant. Then as we go for the moderate temperature, the Kramer's law would be valid, and the Kramer's law relation, the simple t to the power minus 7 by 2 relation will be valid. And if we further increase the temperature and go to higher temperature, the electron scattering will be valid, in which there is almost a constant dependency of kappa on temperature. So this is the graph. Then we just look up to these references. Thank you.